Our night skies are awash with stars. Nestled among them are the familiar planets of our solar system. If we look a little further, we start to see some of the over 5,000 exoplanets that we have so far discovered. Exoplanets are dazzlingly diverse, ranging from gas giants many times the size of Jupiter, to sub-Neptunes, the most common type of exoplanet, to rocky planets, just a little bigger than the Earth. These are called super-Earths. The closest super-Earth we've discovered in a habitable zone orbits a low-mass star, known as an M-dwarf, called Proxima Centauri. M-dwarfs are very active and bombard their planets with radiation. Is there a nearby super-Earth around a star more like our Sun? This is exactly what was discovered by a team led by Dr Shweta Dalal at the University of Exeter's Astrophysics group.
So we have discovered super-Earths around the K-dwarf. K-dwarf is a star which is like Sun but slightly less massive and has a small in size, as well as the temperature of the star is less than our Sun. We discovered 3 planets, all of them are super-Earths, and one of the planet is in the habitable zone of the star. The habitable zone of a star is the distance from the star where the temperature is neither too hot nor too cold. It's just right for the water to be in its liquid form on the surface of that planet. So this planetary system is about 16.8 parsec away from us. If you think about how long it will take for the light from Sun to reach this particular planetary system, it will be more than 50 years. The fastest spacecraft that we have, I would say maybe thousands of years to reach there. So we are not saying closest for us to be there, just in terms of astronomical scale, 16 parsec is pretty close to us, because most of the exoplanets we have discovered are beyond 50 to 100 light years away, basically. This planetary system lays foundation for our next step, which is to discover Earth-like planets. When I say Earth-like planet, we are talking about planets which are of size like Earth and has a mass of 0.5 to 1 Earth masses, and they are in the orbit around their star in a habitable zone like we discussed earlier. So Exeter is part of a big international collaboration, which is Terra Hunting Experiment. Terra Hunting is a most viable experiment in the upcoming decade, which will try to detect Earth-like planets around solar-type stars. The method which Terra Hunting is going to use is called radial velocity method, and it's the same method which we used to detect our planetary system. So you might recall this method from Nobel Prize in 2019, where researchers discovered a hot Jupiter around a solar-type star using the radial velocity method. So to give you an overview of how we detect exoplanets using radial velocity method, when you have a star and a planet, they are both going around each other around a common point which we call the center of mass. Now, in the case of radial velocity method, we are looking at the light coming from the star. So it's an indirect method. And instead of looking at the brightness like we do in transit method, we are actually looking at the spectrum of the star. Imagine your star is going away from you, the starlight would be red shifted, and if the star is coming towards you, the starlight would be blue shifted. Now think of if you have a planet around it. Now because of the planet, you're seeing this wobble. Even this results in slight red shift and blue shift, again depending on if the star is coming towards you, so blue shift, and away from you, red shift. This wobble results in the shift in the spectrum, and you can see this in the lines of the spectrum moving towards red and blue, or in this case you're seeing it towards left and right. And this is the signature of a presence of a planet. So in this case, because we have only one planet, you see a very nice, if you were looking at the radial velocity, you will see very nice sinusoidal behavior. But if you have multiple planets, you can still use this method, because this sinusoidal behavior will be a slightly complicated version, and you'll see small period and a larger period behavior. So you can still detect multiple planets using the radial velocity method. Similar to terra hunting, in past people have tried to have programs to detect smaller planets, and one such program is called Rocky Planet Search on Harpsnot spectrograph at the TNG in La Palma. We've been observing almost 50 stars for 10 years, trying to find smaller and smaller planets using the radial velocity method. Although we had made significant improvement in instrumentation, we have still problem detecting smaller and smaller planets. Just to give an order of magnitude for you, if you were detecting a Jupiter-like planet, we would need a detection of 1 meter per second, which is very good. Our instruments are able to do that. But if you want to detect an Earth-like planet, you need centimeter per second. So for example, for Earth, it is 9 centimeter per second. It's kind of similar to the speed of some of the tortoise species on our Earth. So we are trying to detect a tortoise moving left and right, and it's really difficult to do that. Although our instruments are able to detect up to 30 centimeter per second, we are still not able to reach this 10 centimeter per second accuracy. One of the obstacles in detecting the small signal of 10 centimeter per second is stellar variability. The radial velocity signal that we get from the star is a combination of different components. Of course, you are getting the planetary wobble, but you also get stellar variability, and you also have some sort of instrumental shifts if you're observing for a very long time, and additionally you have Earth atmosphere. So you have to take care of stellar variability, instrument, and Earth atmosphere if you want to detect the planetary signal. And this is exactly what we did it in our recent discovery. So we had different models and different tools to correct for the stellar variability, instrumentation, and Earth atmosphere to be able to detect the 3 planetary signals that we discovered. For exoplanet scientists, I think anything other than planet, we consider it as a noise. So stellar variability, instrumentation, or Earth atmosphere, all of these are characterized as noise for us. So when we are trying to detect exoplanets, so in our case, we had 10 years of observations. So we employed many techniques or models to treat this stellar and instrumental noise to be able to detect exoplanets. This planetary system is super interesting because it's got 3 super Earths, and all these 3 candidates are different from each other. So the closest planet, which is actually in a short period orbit of 7.3 days, is so close to the star, it's probably really hot. It's a very hot planet. Then you have a planet at 38 days. It's actually very close to the stellar rotation. So the star is rotating around 43 days, and these planets take 38 days to go around the star. And if you think about it, the planet actually just looks at the one side of the star. It actually will take 21 years for this planet to actually see the entire surface of its own host, right? So when I said 21 years, it's 21 years for that planet, like, because the 1 year is 38 days for that. And then we have a planet at 151 days, which is in a habitable zone of the star. Another thing which is cool about this planetary system is that we will be able to observe this system using direct imaging in the future. The super Earth candidate, which is in the habitable zone, would be a really good target for direct imaging. For example, you can use the 30-meter telescope to do that. So if you want to know about direct imaging, you can even watch the video of JWST by Sasha Hinckley. This is not the end of the story. We are still observing this planetary system to look for additional candidates. We will also do direct imaging in future and probably look at the atmosphere of these planets using high contrast spectroscopy. Additionally, I would like you to stay tuned for terra hunting experiment, which will probably discover Earth-like planet around solar type stars in the next decade.